Hi everybody! Did you ever ask yourself how the square root function is implemented on your calculator, your computer, or in your programming library? Today I want to show you one way to implement it using binary search, so let's get started. So the first thing that we need is the function itself, which will take a single float as an argument and also return a floating point number. The next step is to add a few assertions for testing. So the square root of 1 is equal to 1, the square root of 4 is equal to 2, and so on. So numbers that are less than 1 are actually a special case, because their square root is greater than the number itself. We need to keep this in mind when we implement our function because it requires special handling. In addition to the hard-coded assertions, we can also use the square root function of the built-in math module to build more comprehensive assertions. To do that, I'm also importing the random module so that we can, in a loop, generate random numbers from which we can calculate the square root using our own function as well as the built-in function, and then we can assert that the result of the two square root functions is the same up to a certain precision. So when I now run the program, it raises an assertion error, and needless to say, this is the expected behavior since we did not yet implement our function. So the first step for the implementation itself is to choose the initial lower and upper boundaries. For the lower boundary this is pretty easy because we can just use 0. A square root can never be negative, so 0 should be fine. And for the upper boundary we can say that in most cases the square root must be less than or equal to x, except in the case where x is between 0 and 1. In this case the square root can be, or will be rather, greater than x, and therefore we choose as the upper boundary x or 1, whichever is greater. The second step of the implementation is to add the loop that we will be using to narrow down our search interval by either updating the lower boundary or the upper boundary. To decide which of the two boundaries has to be updated, we take the square of the middle of the current search interval. If this value is greater than or equal to x, we know that we have to reduce the upper boundary because the middle is already greater than the square root that we are trying to calculate. On the other hand, if the value is less than x, we know that we have to increase the lower boundary because the middle is still less than the square root we are trying to calculate. Last but not least, we need to return the computed square root from our function, and we do this whenever the calculated middle of the search interval is either equal to the lower boundary or equal to the upper boundary. This may seem strange at first sight, but it does make sense if you remember that we are working with floating point numbers. Due to the limited precision of floating point numbers, our loop will pretty quickly run into a situation where a further subdivision of the search space given by the lower and the upper boundary is no longer possible. That said, we now have a working square root implementation. Running our program no longer raises any assertion errors, proving that everything works as expected. At this point, it is easy to generalize our code to compute cube roots or n roots in addition to square roots. In order to do this, I'm very quickly adding a few assertions for the cube root as well as adding an empty function definition. The math module also has a built-in cube root function that we can use again to compare our own cube root function with the one that's shipping with Python. Now I'm renaming our square root function because this is the function I want to generalize, and both our square root as well as our cube root functions will delegate to the generic one. So pretty much the last thing that we still need to do is to add an additional argument to our generic root function to pass in the exponent that we want to work with. For the square root this would be a 2, and for the cube root this would be a 3. That's it. Now when we run our program we don't get any assertion errors reported, meaning that both our square root as well as our cube root functions are correctly implemented. If you found this video interesting, please leave a like and subscribe. And if you have any questions, please leave a comment as well. Thank you for watching and see you soon. Bye bye.